Hello everyone. Today we are going to explore some of the key concepts in networking that are foundational to understand modern mobile networks. From 2G to the upcoming 6G, we will trace the evolution of these technologies and explain why they are important. So let's dive in. We will be talking about virtualization, VNFs or virtual network functions, SDN or software defined networks, orchestration, and cloud native architecture. Our journey begins in the 1980s with the advent of the 1G and 2G mobile networks. Back then, networks were built using physical network functions or PNFs. These were hardware devices like routers, switches, and firewalls, developed and provided by companies like Cisco and Juniper Networks. They performed specific network tasks and were essential for the initial phase of mobile communication. These physical devices were reliable but inflexible. Each new service or upgrade required significant physical changes and investments, which made scaling and innovation cumbersome. In 2G GSM networks introduced in the early 1990s, mobile networks began to offer digital voice and basic data services like SMS. The network architecture consisted of base transceiver stations or BTS, base station controller or BSC, and mobile switching centers MSC. All these components were hardware based, forming the backbone of early mobile networks. Fast forward to the early 2000s. With the introduction of 3G networks, the demand for data services grew exponentially. This period saw the rise of virtualization. VMware, founded in 1998, played a significant role in this transformation. Virtualization allows us to create virtual versions of physical resources. Instead of running one application per server, multiple virtual machines or VMs can run on a single physical server. This maximizes resource utilization, reduces costs, and enhances flexibility. In mobile networks, virtualization enabled the creation of virtualized core networks, such as the Virtualized Evolved Packet Core or VEPC in 4G. This separation of hardware and software allowed operators to scale their networks more efficiently and reduce operational costs. While virtualization is often associated with virtual network functions, it is important to note that virtualization can exist without VNFs. For instance, in data centers, virtualization is widely used to create virtual servers and storage. These virtualized resources enhance flexibility, allowing organizations to quickly adapt to changing demands and optimize their hardware utilization. As we moved into the 4G era, the concept of virtual network functions (VNFs) emerged. Around 2012, European Telecommunications Standards Institute (ETSI) introduced Network Functions Virtualization (NFV), which advocated for VNFs. VNFs are software implementations of network functions that used to be hardware based. These functions like firewalls, load balancer, and routers now run as software on standardized hardware. This shift allowed for greater flexibility, quicker deployments, and more efficient scaling. In 4G networks, VNFs become a core component. The VEPC or virtual EPC, for instance, consists of several VNFs, including the MME or mobility management entity, serving gateway, and packet gateway. These VNFs can be dynamically managed and scaled based on user demand. Around the same time when VNFs were being developed, software defined networking or SDN started gaining traction. SDN was pioneered by researchers at Stanford University in the mid 2000s and commercialized by companies like Nicera, which was actually later acquired by VMware in 2012. Let us see core concept of the SDN. To start with traditional network, in the traditional network model, network devices such as routers and switches have their control plane and data plane tightly coupled. This means that decisions about where traffic is sent are made by individual devices themselves. But in SDN decouples these planes, allowing centralized control over the network through a software controller. While SDN gained prominence in data center and enterprise environments, its principles have also been applied to mobile networks, enhancing their agility and efficiency. In the mobile networks, SDN can optimize traffic flows, manage network congestion, and ensure quality of service for different applications. For example, in 5G, SDN helps manage the network slices that cater to various services like EMBB, URLLC, and MMTC. With the rise of VNFs and SDN, managing the growing complexity of networks became crucial. This is where orchestration comes into play. Companies like OpenStack and Kubernetes have been pivotal in this space. Ever wondered why term orchestration? Yes, let us have an analogy from the orchestra. The term orchestra in networking is used because it captures the essence of how various components within a network work together in a coordinated and harmonious way, similar to a musical orchestra. Let us devote some time in understanding orchestration. Orchestration involves the automated arrangement, coordination, and management of network resources. It ensures that VNFs and SDN components work together seamlessly, automating tasks like deployment, scaling, and recovery. This is essential for maintaining efficiency and reliability in modern networks. At NFVMANO or network functions virtualization, management, and orchestration. It is a framework from Etsy that standardizes how to manage and orchestrate virtual network functions for flexible and automated network services. Now let us understand this analogy clearly. For an orchestra, very first thing we need is the stage or venue where the orchestra performs, where various resources are kept and can be used when required. So we have NFVI or Network Function Virtualization Infrastructure. It comprises the physical and virtual resources that form the foundation of this NFV environment. It includes compute storage and networking resources as well as hypervisors, virtual switches, and other virtualization technologies. The NFVI provides the platform on which virtualized network functions are deployed and run, supporting the delivery of network services. If we have a venue, we need to have a venue manager who ensures that the concert hall's resources are properly allocated and managed. In the NFV context, we have VIM, Virtualized Infrastructure Manager. VIM manages the virtualized resources within the NFVI, ensuring that they are available and optimized for the VNFs. Next comes the musician. Musician uses the resources provided in the hall, like chair, music instrument, music sheets, to play the music. In the NFV concept, we have VNF, Virtual Network Function. Each musician plays a specific instrument and contributes to the overall performance. In the NFV context, each VNF provides a specific network function, such as firewall, load balancer, or router. When combined with other VNFs, it delivers a complete network service. In the orchestra, For each group of musicians, like the musicians playing violin, will have one lead violinist who ensures that their group of musicians is prepared, in tune, and ready to perform their part. In NFV, we have VNFMs. The VNFM or Virtual Network Function Manager manages the life cycle of that VNF instance. It handles tasks such as instantiation, scaling, monitoring, and termination of VNF. Now, there is main orchestrator in an orchestra who coordinates the entire performance. He sets the tempo, interprets the score, and ensures all sections work together harmoniously. In this architecture, we have NFVO as orchestrator. NFVO or Network Function Virtualization Orchestrator. The NFVO orchestrates the instantiation, management, and lifecycle operations of network services across the NFV infrastructure. It coordinates the provisioning and management of resources and services, interacting with the VIM to allocate resources and with the VNFM to deploy and configure VNFs. It ensures the efficient and coordinated operation of the NFV environment. The VNFM communicates with NFVO to receive instructions for deploying and configuring VNFs, ensuring that they operate effectively within the NFV infrastructure. The network service is the music performed by this orchestra. The music represents the end result of all the musician VNFs working together under the guidance of the conductor NFVO and section leaders VNFM within the concert hall NFVI, which is managed by the stage manager VIM. The VIM ensures that the concert hall's resources are properly set up and optimized, supporting the musicians in delivering a harmonious performance. It is a cohesive output that delivers value to the audience. This table summarizes the orchestra analogy we discussed. You can pause and have a look. As these technologies evolved, the cloud became an integral part of the networking landscape. Cloud computing, popularized by companies like Amazon Web Services, Microsoft Azure, and Google Cloud, offers scalable, on demand computing resources over the internet. The cloud provides infrastructure as a service, platform as a service, and software as a service, which enable network operators to leverage vast computing and storage resources without maintaining physical infrastructure. In mobile networks, cloud technologies have revolutionized the deployment and management of network functions, which enables what is known as cloud native architectures. Let us break this down in the context of mobile networks, particularly 5G. For mobile network operators, infrastructure as a service eliminates the need for expensive and dedicated hardware. Operators can deploy core network functions such as packet gateway MMEs in the cloud. This allows for rapid scaling up or scaling down based on demand. It optimizes resource use and reduces cost. Let us see some of the applications. Network slicing. Infrastructure as a service supports the concept of network slicing in 5G, where multiple 5G networks can be created on a shared physical infrastructure. Each slice can be customized to meet specific requirements of different use cases, such as ultra low latency communication, industrial automation, or EMBP. Edge computing integration. Infrastructure as a service enables the deployment of edge computing nodes, which are crucial for 5G. By bringing computing resources closer to the end users, edge computing reduces latency and enhances performance for real time applications like augmented reality, virtual reality, and autonomous driving. Dynamic resource allocation. With IaaS, 5G network can dynamically allocate resources based on real-time demand. For example, during a large public event, additional computing resources can be provisioned in the cloud to handle the surge in network traffic, ensuring consistent quality of service. And last is core network functions. Infrastructure as a service supports the deployment of core network functions such as the 5G core components, which include the access and mobility function or AMF, SMF, and UPF. These functions can be dynamically scaled and managed in a cloud environment, providing flexibility and resilience. Platform as a service provides a platform allowing customers to develop, run, and manage applications without dealing with the underlying infrastructure. Let us see some examples. VNF deployment and development. PaaS environments like Kubernetes and Docker provide the tools for developing, testing, and deploying VNFs as a microservice. This ensures VNFs are easily manageable, can be updated frequently, and are highly resilient. Next is DevOps integration. Platform as a service enables DevOps practices, facilitating continuous integration and continuous deployment of VNFs. This ensures that new features and updates can be rolled out quickly, enhancing the agility of 5G networks. AI and machine learning integration. PaaS platforms often include capabilities for AI and machine learning, which can be used to develop advanced network analytics and management applications. These can optimize network performance, predict failures, and automate responses to the network issues. Last is service creation and management. Platform as a service provides the flexibility to rapidly create and manage new services on top of the 5G network, such as IoT services, smart city applications, etc. Software as a service delivers software applications over the internet on a subscription basis. SaaS models can provide various network functions and services such as network monitoring, security, and management tools. Operators can subscribe to these services, reducing the need for in-house solutions. Let us see some applications. Network monitoring and analytics. SaaS applications can offer real-time network monitoring and analytics tools, providing operators with insights into network performance, user behavior, and potential issues. These tools can predict and mitigate network problems before they affect users. Security as a service. Security application delivered as SaaS can protect the 5G network from cyber threats. These services can include intrusion detection system, firewalls, and security information and event management systems that are continuously updated to address the latest threats. Customer experience management. SaaS solutions can enhance customer experience by providing tools for managing customer interaction, service, quality, and feedback. These help operators ensure high levels of user satisfaction. Service orchestration and automation. SaaS can provide advanced orchestration and automation tools, allowing operators to efficiently manage network slices, automate service provisioning, and optimize resource allocations. To summarize, cloud technologies empower mobile networks by providing scalable, flexible, and efficient platforms for deploying network functions. This cloud native approach is crucial for advanced capabilities and demands of 5G, and it sets the stage for future innovations in the mobile networking. The evolution of mobile networks has been profoundly influenced by several key technological advancements. We have seen virtualization, virtual network functions, software defined networks, orchestration, and cloud native architecture. These technologies have collectively transformed mobile networks from rigid hardware dependent system to highly flexible, efficient and scalable infrastructures. It enables rapid deployment and development of new services. As we look towards 5G advanced and 6G, these technologies will remain crucial. 5G advanced will enhance performance, reliability, and efficiency with improved network slicing, enhanced edge computing, and AI driven network management. 6G, which is expected in 2030s, will offer unprecedented speed, ultra low latency, and massive connectivity. It will utilize advanced virtualization, VNFs, orchestrations, and cloud native principles to support applications like holographic communications, immersive AR, and pervasive AI. 6G networks will be highly adaptive and self optimizing. Thank you for reaching till here. So, in this video, I tried to stitch this story piece by piece, just to give brief introduction about these technologies which have actually led to advancement in the mobile networks and how these are very crucial for further advancement in mobile networks, and these technologies are going to play significant role in revolutionizing the mobile networks and what we can call as next generation or the modern mobile networks. So that was my effort. Thank you for watching till here. I'll see you in the next video.